As the Earth's population continues to grow and develop, our limited freshwater resources become increasingly scarce. We are fortunate that the Earth's oceans offer an alternative and can provide a sustainable supply of potable water. Seawater can be economically and reliably converted to potable water through a process known as seawater reverse osmosis. The process starts by extracting water from the ocean using wells located on the shoreline or by using an intake structure located in the open ocean. Osmosis is a naturally occurring process where a solvent, such as water, passes through a semi-permeable barrier. The semi-permeable barrier, or membrane, allows some things to pass through it, but not others. In nature, the direction of flow through the membrane is from a less concentrated solution, such as fresh water, to a more concentrated solution, such as seawater, until equilibrium is reached. Reverse osmosis is when the opposite occurs. By pressurizing the concentrated solution, the seawater, we are able to force water molecules to pass from the salty seawater solution through the membrane to the fresh water. To protect the reverse osmosis membranes from becoming clogged by solid particles that can be suspended in the seawater is filtered before passing through the membranes. This is accomplished by using multimedia filters, which are tanks or vessels containing a series of layered granular materials. These materials can be anthracite, garnet, sand, pebbles, and/or gravel, which are assembled in layers. The filters remove sand, twigs, seaweed, and other particles from the seawater. In some cases, other types of membranes, known as ultrafiltration and microfiltration membranes, are used instead of multimedia filters to pre-treat the seawater. Next, the filtered seawater travels to the cartridge filters, which act as a second stage of filtration. Cartridge filters used for seawater reverse osmosis are typically made from a yarn-like synthetic material that is wound into cartridges. These remove even smaller solid particles from the seawater, such as fine sand and clay, before the seawater proceeds to the reverse osmosis membranes. High-pressure pumps increase the pressure of the seawater up to 1,000 psi. The pressure needs to be sufficiently high to overcome the naturally occurring osmotic pressure and force water from the saltwater side through the reverse osmosis membranes to the freshwater side. The salt particles in the seawater are rejected from passing through the membrane to the freshwater side and remain behind on the concentrated saltwater side. The reverse osmosis membrane can be thought of as a number of sealed envelopes connected at their open ends to a tube. There are spacers between each envelope which allow water to flow across the membranes. The membrane envelopes and spacers are then wound around the tube like a roll of paper towels. The reverse osmosis membranes are then enclosed in a fiberglass shell. The membranes are connected end to end, usually 6 to 7 membranes together, and housed in vessels that are built to withstand pressures up to 1,200 psi. As the pressurized seawater enters the pressure vessel and flows across the membrane surface, the water molecules are forced into and through the membrane envelopes, leaving the salt molecules behind. The desalted water passes through the membrane and emerges at low pressure, where it is collected in a tube and directed to one end of the pressure vessel. The concentrated salt stream that is rejected from flowing through the membrane continues to pass across the membrane surface, where it is collected separately. The concentrated salt stream retains about 55% of the total energy of the seawater stream that was originally fed to the membranes. To reduce the energy that is required to operate the reverse osmosis plant, the pressurized concentrated stream is piped into an energy recovery device. Here, up to 98% of the energy of the concentrated salt stream is transferred to an equal volume of the incoming seawater in an isobaric energy recovery device. The energy recovery device significantly reduces the plant's operating costs by recovering the concentrated salt stream energy and using it to pressurize 60% of the seawater that is fed to the membranes. The concentrated salt stream will have about a 60% higher salinity than the incoming seawater. The concentrated salt stream is sent back to the ocean through a brine disposal well, or a device known as a brine outfall. The brine outfall is situated in an area of significant ocean flow so that the salt levels are quickly returned to equilibrium with the ocean. The location for the outfall should contain no sensitive marine ecosystems. In a properly designed brine outfall, no noticeable increase in salinity can be detected at a distance of a few meters from the discharge. The pressurized seawater leaving the energy recovery device has its pressure boosted by a small booster pump so that it is at the same pressure as the seawater leaving the high-pressure pump. The boost is necessary as some pressure has been lost as the stream travels through the reverse osmosis system. Approximately 40% of the seawater that enters the system is converted to potable water during the reverse osmosis process. The potable water is further treated by adding calcium carbonate to improve the taste and bring the pH to the neutral range. Chlorine is also injected to provide disinfection properties as the water travels from the reverse osmosis plant through the distribution pipes to homes and businesses. When proper conservation of natural water resources is practiced, water reuse has been applied, and a water deficit still remains. Seawater reverse osmosis can offer a sustainable alternative. With good stewardship, it can provide life-sustaining water for coastal communities. Desalted water supplies, which are not susceptible to drought and other natural disasters, can provide a clean, safe potable water supply.